which is that which was a principle first enunciated by Fermat. And yes, this is the same Fermat who scribbled theorems in the margins of his notebook and then said that this would be trivial to prove. And then that theorem took almost a few hundred years before we finally got the proof, which you might all be aware of. It's called Fermat's last theorem. And anyway, but this same Fermat also made very critical contributions in many different physics fields, including in optics, where you could say he rediscovered, but he made more specific a principle that Hero of Alexandria had initially also figured out, which is that light seems to propagate, the ray in which the path that a ray of light follows is such that the value of the path integral of the refractive index, n of r, along the path of the ray is smaller than all other possible paths. And so you see here two different paths. One is gamma and one is gamma prime, going through some medium with some refractive index n of r. And we see that, excuse me, that the integral of n of r along the path, which is the solid line, is smaller than along gamma prime. I'm not saying that, I'm just saying out of these two paths, if it is smaller along gamma, it will follow gamma rather than along gamma prime. Okay. This quantity n times distance, n of r times the distance along the ray path, is called the optical path length. Okay. And there's very strong analogies here that we won't go into here, but if you take a classical mechanics course, you'll see that there are many analogies to the minimum action principle. So you can define something called an action, which is a function of the path. And the minimum action principle says that particles follow trajectories such that they minimize the action. So this is, of course, a different way of looking at how a particle or a beam of light propagates than traditional Newton's method. In Newton's differential equations method, the position of particle at some point P here, for example, and if you know its velocity and its position, then you can predict in the next instant delta t where the particle will be based on some differential equations. Here, we're making a statement about the entire path through this method of the optical path length. And these kind of statements about the whole path, and so this is called a functional of the path, because this entire quantity depends on the path itself. So we have to evaluate it for all the different paths and then find the one that has the minimum value. And this general field itself, where people evaluate what are the minimum or extremum values of a functional, is called the calculus of variations. And you will learn about that, as I said, when you take more advanced mechanics classes. The corollary, of course, is that in a free space or a uniform space of constant refractive index n, light will propagate in a straight line. And the consequences of that then are the laws of reflection. And as I'll show you, the laws of reflection and refraction both come out of the minimum path or Fermat's principle. The one thing I should mention is that many times you'll hear it referred to not just as the minimum path or optical path length that is minimized. You'll also hear about it as the least time formulation, meaning principle of least time. And the reason for that is straightforward. N is equal to C over V, as we have learned from wave motion. The refractive index is defined by the velocity in vacuum divided by the velocity in the medium. So that means that this index becomes C divided by V times dl, and that dl over V is just time, right? Distance divided by velocity is time. And so this is referred to as the principle of least time, and that's principle of least time. And there's one more subtlety, which most of the time does not matter, but I just wanted to make it stated correctly here. The real statement of Fermat's principle is that the optical path length or the time must be stationary. That is, it's either a minimum or a maximum. Okay, so that's the real principle. It's not necessarily least. It could be a maximum sometimes, but most of the time, and which one it is will depend on the situation. You'll have to evaluate it to see what it is. But and that can happen in some situations. They're kind of weird, but it can arise where the path is maximum rather than a minimum. Now let us then describe, or let us show that Fermat's principle implies that the reflection angle and the incident angle must be the same. So to do that, I'll start with the mirror surface. So this is M prime defines the mirror surface. I'm going to assume for now that we can take that the incident and the reflected beam are in the same direction, are in the same plane as the normal. And here is the point A and the point B, and that's the point B, sorry. And yeah, and the question is, we have this angle theta I. Oops. And we have this angle theta R, and our goal is to show that theta I equals theta R. Okay, and remember our aim or our process for doing this is to consider all the passable paths that go from A to B and that hit the mirror. Of course, the shortest possible path between A and B is simply a straight line that connects A and B directly. So, you know, this path here would be the shortest path of all. But we want to have the beam of light undergo reflection from the mirror, but it could have hit the mirror, say, at a point, say, E over here, and then made, you know, a path like that, or it could have gone directly down to the point D over here. So let's call this D, this is E, and it could have made a path over there. And so how do we know that the shortest path is the one that I've shown you, which hits at the point C, and then goes to the point B, and that is indeed the shortest path from A to B after reflection at the mirror. So this is somewhat not so difficult, because what we can do is we can imagine we can make a new point B prime that is on the other side of the mirror MM prime, and it's the same distance and at the same lateral position, so to speak, as B. So here is B prime, which is basically exactly the same distance away from the mirror M prime, but on the MM prime, but on the other side of the mirror, and is at the point B prime now. And so now it's easy to show, or you can see quite easily because of the how I've drawn B prime to be exactly the same distance away, that any distance from, say, E up to B is the same as the distance from E to B prime, right? It has to be, because B and B prime are symmetric around the mirror. So the distance EB is the same as the distance EB prime. The distance DB and DB prime are the same, and CB and CB prime are the same. And so therefore, out of all the paths from A to B that hit the mirror and go back to B, they are the same as the paths that go and hit a point on the mirror and then travel to the point B prime. And so now the question is much more straightforward. What is the simplest or the easiest, the shortest path from A to B prime, which will obviously go through the mirror, and that is the one that goes in a straight line from A to C to B prime, sorry. And so because, and let's call this point here also where B and B prime intersect the mirror as F, okay? So if you want to make it more formal, since angle BFM is equal to 90 degrees and BF is equal to B prime F, you immediately see that EB prime must be equal to EB because they're just the hypotenuse of those triangles, EBF and EB prime F. So this just proves that for any point, the statement that I made earlier. So therefore, we can also now show that AE plus EB is equal to AE plus EB prime. Okay, so it's the same, which is just, I'm just formalizing the argument that I made earlier that we can replace all the paths that go from A to B via the mirror to those paths that go from A to B prime via the mirror. Okay. Then, so we can also now, and since clearly we can just draw a straight line from A to B prime that intersects the mirror at the point C, now all that's left to do is to show that this implies theta I equals theta R. Okay. So this is again fairly straightforward because A, C, B prime is a straight line. I know it doesn't look very straight, but it is a straight line, right? We can draw a straight line. So that means the angle B prime CF, which is this angle, and ACM, which is this angle, must be the same. Okay, when two lines, that is the line ACB and MM prime, they meet at the point C, then the opposite angles are equal. Okay, and similarly, because the angle B prime CF and ACM are equal, as I just showed you, we can also show that because the two mirrors, the two triangles, that is triangle CFB, this triangle, has the same angles, right, as this, has the same sides rather, as this triangle, that is the triangle B prime CF. By construction, those two triangles are symmetric. In fact, they're what are called similar triangles, right? Because of that, this angle and this angle must be the same. So they share the same 90-degree angle, and then two of the sides, that is B F and B prime F, are the same, and CF is shared. So that means two sides and an angle are the same, which means that these two triangles are similar, which means all the angles inside these two triangles are the same. So B prime CF and BCF are the same. So I'll just formalize that. So triangles BCF and B prime CF are similar because, as I just showed you, they share two sides equal and one angle that's the same, and that makes all the angles automatically the same. So because of this, so the triangles, these two triangles are similar, which, as I just said, makes angle BCF equal to angle B prime CF. Okay. And now we can immediately draw some conclusions, because this is the angle theta R. So this must be 90 minus theta R. Okay. And this angle I just showed you is the same as this guy over here, which is the angle ACM, and B prime CF, I already said, has to be equal. BCF equals angle ACM, okay, which implies 90. And this guy is the same as 90 minus theta I. Okay, so what we have just done is shown. So if on this side this is 90 minus theta R, and because BCF equals angle ACM, which implies BCF is also equal to 90 minus theta I, and therefore theta I equals theta R. Okay, so that is our proof on the basis of this geometrical construction and Fermat's principle that the reflected angle and the reflected angle and the incident angle are the same. Okay. Then the last point to note is that if an observer is at A and the object at B, or vice versa, whichever way you want to look at it, then the because we made this construction, B and B prime are equivalent. They are they are equivalent points as far as A is concerned. So the observer thinks the object is at A. Sorry, is at B prime, which is inside the mirror. It's as if there were no mirror, and you see essentially what I've said here is you see the reflection of B at B prime, which is exactly equidistant from the mirror as B is from MM prime. Okay, so we've also shown that the image point B prime is the image of B in the mirror and is equidistant and is equidistant from the mirror. Okay, so now we move on to the law of refraction. So in this part, imagine that this is air and this is glass. So now we have that the beam of light is traveling from air into glass and has to go from point A to point B, where B is inside the glass. Okay, and once again, I've drawn the normal to the surface, to the interface, which is NN prime, and then I'm showing the various points along. I'm characterizing where the beam hits the surface that has a coordinate which I'm calling y in this case. Okay. All right. So why? So our question is, and this is actually very similar to a problem that, say, a lifeguard might face. Because remember, you can think of this as air glass or even air. Let's say it's air water, right? This makes it a little bit similar to what a lifeguard might experience. If they see a person at the point B, so the lifeguard is at point A, and they see a person at point B who's struggling, and they need to go rescue that person. And in general, most human beings, we can run faster on sand or air or on earth than we can swim in the water. And so the problem that the lifeguard has is what is the best route that they should take to get to the person who's drowning at the point B in the least amount of time. Okay, so if I were to plot time t versus y being where the lifeguard should get into the water, should jump into the water to start swimming, you might say, well, okay, so if I obviously say a path like AXB seems like it would not be so good, because the lifeguard is spending a lot more time in the water than they are in the air. So if I were to plot t, which is the time for the rescue, versus y, we expect some kind of shaped curve like this, where if the lifeguard gets into the water at the point X, they ran really fast from A to X, but now they have to spend a longer time in the water from X to B. And similarly, if they go the other way, where I'm drawing another path, let's call that some other point D. Now they spend very little time in the water because they've gone fast, but they've increased the time that they spent in the air on the sand, and even if it's faster, it may not be enough to make up for the extra distance that they've traveled in the air or on Earth in this case. So somewhere in here, in this region, is the point C, which is the least amount of time. And this is the exact same thing that's happening to a beam of light, because as we know, the refractive index between air and glass, or air and water, air has refractive index 1, water has refractive index 1.3, glass is 1.5 approximately. So, and we know that the velocity goes as c over n. So the higher the refractive index, the slower the velocity of light in those media, and therefore it's exactly like the lifeguard analogy of how much time and which path to take to get to the point A to B in the least amount of time. In fact, as you can see from this curve, as we move the point X nearer and nearer to C, you can see that the point C is such that to first order, the curve essentially starts to look flat, stationary, basically, as a function of time, as a function of the y coordinate. The time looks stationary. Essentially, the derivative of the time becomes close to 0 near the point C, which is, of course, what we mean by stationary to begin with, that, in fact, the derivative of some attribute, like the time in this case, is starting to become 0 with respect to changes in the path near this point of extremum, this point of where Fermat's principle says will be the optimal point for light to travel. And so therefore what we can do is simply set up, so there are two ways to approach this problem. One is actually to use a geometrical construction, just like the one we did for the reflection. We can set up geometrical constructions, we can look at similar triangles, but it does get a bit complicated. So instead, what we'll do is we'll simply set it up as a differential equations or differential problem, because we can write down exactly the formulas. So let's call the distance A from the surface to the point A, and the distance here is B, and the distance of this C, the point where the ray crosses the crosses the y axis, that distance I'm going to call x, right? Because what we need to know is what is the location of point C, which are given by the coordinate x here. So maybe I should just have said x right from the beginning. Sorry about that. Let's just call this x. Which made more sense anyway. And so we have now the angle theta I. Notice how the angle theta I is defined. This often trips people up. It's with respect to the normal to the axis, not the angle from the ray to the surface. The surface is along this x-axis here, okay? So that angle is 90 minus theta I, the incident angle. Similarly, the refracted angle, theta R, in this case, is, and I guess I promised I would use theta 1 and theta 2, just to avoid this confusion between incident and reflected and refracted and so on. So theta 1 and theta 2, okay? And yeah, so the point that I was trying to make is that the angles of theta 1 and theta 2 are always defined with respect to the normal to the interface. So when you measure these angles, you have to be very careful not to mix them up with the angle which is between the ray, the incident ray here, and the refracted ray or whatever. You shouldn't measure them with respect to the surface. That is, you shouldn't take the angle from the surface to those rays, but always from the normal to the surface to the rays. Okay, we can set up the problem now. This is a 90-degree angle right here, and we can exactly see what the distance AC is on this. The distance AC is just square root a squared plus x squared, and the time t1 that the light ray travels in the medium n1, which has a velocity v1, not v1 squared, but v1. Okay, that is the time that it takes this ray to travel in the top medium, which may be air, for example. Similarly, t2, now to locate the point t2, we need to also know the distance between the origin, the coordinate system, and the point B on the x-axis, which is this distance d. And so we see that this distance is b squared plus d minus x the whole square, right? Because again, we have a right triangle here, which is b, and we want the distance bc, and that distance is just d minus x, which is this distance over here, whole squared, plus b squared gives me the hypotenuse of that right triangle, which is over there, and that is going to be the distance bc. And then again, we divide that by v2. Okay, so now all we have to do is we write the total time, which is just the sum of t1 plus t2. And now we want to differentiate this with respect to x. And well, this is a pretty standard differentiation, so I'll just go over it really quick. I would normally get 2x, but then I also get a 2 in the denominator because a squared plus x squared to the whole power half is just going to pull down a 1/2. And so that's that half and the 2x will cancel. And then similarly here, you're going to get minus d minus x, minus sign coming from the d minus x inside that, and there's a v2 square root b squared plus d minus x the whole square. Okay, and we can see from the geometry of these angles that the value x divided by square root a squared plus x squared is simply sine theta 1. So you can see that right here. So this is x, and a squared plus x squared was that hypotenuse over here, and which is also the same as this hypotenuse here, and so we see right away that that's cosine of the angle theta I, sine of the angle theta I, sorry, because it's cosine 90 minus theta I, which is sine theta I. Okay, and similarly, d minus x by square root b squared plus d minus x the whole squared is just sine theta 2. And so, and then we can also replace v1 as c over n1 and v2 as c over n2, and that is going to give me n1 sine theta 1. And this all has to be set equal to 0, the derivative, for an optimal or extremal point. So that gives me the law of refraction, which is also known as Snell's law, because in, let me see, which year was that? In 1621. A Dutch physicist named Willebrord Snell found this rule, and he just found it as a relationship between angles, from which he concluded that this, which was made constant by these n1s and n2s for the medium, So, he plotted the angles and found that they were always in a constant ratio as long as the media was defined. So air and glass always had the angles in this ratio. And similarly, air and water had always the angles in the same ratio. Anyway, so that brings me to the stopping point for this part of the video. Okay, so today's lecture, I'm going to talk about a few topics that are consequences of the laws of reflection and refraction, as well as from our understanding of Fermat's principle of least time, or least minimum optical path length. But before I do that, I just wanted to check if everybody had a chance to view the supplementary lecture on that was supposed to precede this one, which is on the derivation of laws of reflection and refraction using Fermat's principle. And does anybody have any questions for me there? Since I put that into a video rather than, because it's mostly the algebra and the geometry of understanding how to use Fermat's principle. So I put it as a supplementary video. If anybody has questions, I'm happy to go over them. Okay.
Question.
Yes. Yes.
Can you talk about the curve?
Which curve?
T versus Y.
Yeah.
It's like
I mean, I was just trying to illustrate that if you have the time for the two different paths, then it's clear intuitively that one of them, when you go too much in the land and then, or if you go a very short distance on land and then go in the water, then that's going to be a longer time. And then similarly, if you go the other direction where you run most of the time and then swim in the water the shortest amount of time, well, that's also going to be our shortest distance in the water. That's still also going to be higher because you spend too much time running to a point that's further away from the person. So it wasn't meant to be a rigorous argument. It's just intuitive that must be the situation, and then there must be some intermediate point where things are, optimal, so to speak. Okay, so in that case, let me talk about total internal reflection. So I'm mostly going to use the chalkboard for that. So let's share for a second. So we've discussed now the law of refraction quite a bit. And let's say that this is a piece of glass. And there's an incident beam of light, laser, or just a beam of light, white light, etc. Incident on this piece of glass. You know that we can now draw the normal to the surface of the glass. Everything I've drawn is obviously in 2D, but you should think about this as a 3D. So we know everything is confined to the plane of incidence by the law of reflection. And how many beams are there now at this interface with the incident light, and how many other beams are going to be there? Total 3, right? That's what you were trying to say. So there's the refracted beam, right? And then there is a reflected beam. And we know from the law of reflection that if this is called this θ1, then this angle is also θ1. And we call this the refracted angle, that's θ2 or θt. I'll interchange between these all the time. And let's say that this glass or surface or medium has a refractive index N2, and the incident medium has a refractive index N1. Okay. And the point I want you to take away is always these two phenomena are going on simultaneously. Reflection and refraction are always happening at all these interfaces where there's a change in the refractive index. Okay. So the reflected beam may be faint. For example, when you look through a very clear pane of glass, you may not see much of a reflection, but it is there. Okay, and it typically, actually, as we'll see later on in the course when we discuss Fresnel's coefficients, that this is roughly about 4% at normal incidence for glass. Okay, so 4% of the light is always getting reflected back in intensity. for a glass pane or a glass surface. But then the rest, 96% of the energy is being transmitted through in the transmitted beam, which we call the refracted beam over here. And we know from Snell's law that N1 sine theta 1 is equal to N2 sine theta 2. So now I'll just make a few observations, which may be already fairly obvious to you, but it's worth going over them in a little bit of detail in case you hadn't thought about this before. So the first is, let's say N1 is lesser than N2. So I'll take the case N1 lesser than N2. Okay, so that's pretty usually the situation: air, glass, air, water, etc., and so on. And in that case, well, we can see from this equation that sine theta 1, which is equal to, or sine theta 2, the refracted angle, that is this angle over here, the refracted angle, is equal to N1 divided by N2 times sine theta 1, which means that sine theta 2 must be lesser than sine theta 1. Now, what does this mean? Well, between 0 to 90 degrees, the sine function, right? So this is pi over 2 or 90 degrees. Between these angle between zeros and pi over 2, the sine function is an increasing function, monotonically increasing. And why do I pick 90 degrees? Well, at 90 degrees, what happens, of course, if I had a different colored piece of chalk, is there any colored piece of chalk there? Right? Maybe I'll have to bring some colored chalk. Okay, so I don't have a colored piece of chalk, but if you just look at a beam of light that's at nearly 90 degrees incidence, right? 90-degree incidence, remember, means that the normal and the beam make an angle of 90 degrees, which means the beam is almost parallel to the surface. Okay, and if you ever looked at water or a pane of glass at nearly glancing incidence or grazing incidence, as it is called, which is exactly this, where you're looking almost edge on at the piece, you can see almost anything becomes a very good reflector. Even, the cover of your book, the cover of your laptop is obviously metal, but almost anything can look nearly reflective when it's at a 90-degree incidence angle or viewing angle, right? So at this point, in fact, like a stone that's skipping over the surface of water, right? The beam of light will just skip over the surface and come and get reflected. Okay. But coming back to my point, that between 0 to 90 degrees, which is when the beam of light is incident either perfectly normal, so 0 degrees, remember now, will be when the beam is perfectly normal to the surface. That's called normal incidence. Okay, and grazing incidence or glancing incidence is when the angle is 90 degrees. So those are the two extremes over here, 0 and pi over 2. In between these angles, sine theta is a monotonically increasing function. What that means is if sine theta 2 is lesser than sine theta 1, which is, if I draw sine theta 2 here and sine theta 1 over here, right? So sine theta 2 is lesser than sine theta 1. We can see from this graph that theta 2, right, which is the corresponding point on the x-axis, theta 2 must be lesser than theta 1. Okay. And what that means here is that if theta 2 is always lesser than theta 1 for n1 lesser than n2, that means that theta 2, the refracted ray, bends towards the normal. It makes a shallower angle with the normal than the incident beam. Okay. So we also say that the refracted ray bends towards the normal. Okay, that will be a common terminology that you might see. Okay, now let's take the other case, n1 greater than n2. Well, what is that situation? Well, it's the opposite situation. Let's say I take a piece of glass or water, etc., any medium which has a refractive index now n1, which is the medium of the incident beam, right? Again, I draw the angles. Now the incident beam now is in a medium n1, which is greater than n2. By the same argument, theta 2, this angle over here, and this is theta 1, theta 2 must be greater than theta 1, right? For n1 greater than n2. Okay. And in fact, now as you keep increasing the angle, okay, so again, I wish I had different color chalk here, but if I keep increasing the angle of theta 1, you will see that eventually theta 2, because it's now always greater than theta 1,
can approach 90 degrees. Okay. And what happens once θ1 goes past that angle, okay, which we'll call the critical angle? Well, as I said, in this situation, I drew it as though there was no reflected beam, but remember, there's always a faint reflected beam going off at that interface. All that means is that there's no more transmitted beam, and all of the energy goes into the reflected beam, which you've all seen now in experiments. Okay. So that is the interpretation of what happens. So, and now we can easily find this critical angle, sine theta c, n1 sine theta c. So the critical angle refers to the angle of incidence, okay, where the refracted angle is 90 degrees. So we put is equal to n2 sine 90 degrees. That's just equal to n2, right? And therefore, we have sine theta c is equal to n2 divided by n1, or theta c is equal to sine inverse n2 divided by n1. And now for air and glass, okay, so n2 is equal to 1, n1 is equal to 1.5 approximately for glass. Theta c is equal to the sine inverse of 2/3, right, approximately. And this is approximately 42 degrees. Okay. So for angles of incidence in a glass material, which is greater than theta c, this 42-degree angle, we'll get perfect reflection. Okay. Even though, as I said, that usually the incident beam, even though usually I've said that the reflected beam is usually much weaker than the refracted beam, above these angles, the reflected beam becomes perfect. It has all the energy of the incident beam, and there is no transmitted beam. The transmitted beam disappears. Okay, that's total internal reflection. Any questions on this topic so far?
So last time I talked about the negative inflection. So is that
negative refraction? Yeah, I'm not talking about that.
Yeah, so the light travels this way, but not to the other, but it's like
it goes the other
way. So how do we so for this material, so how do we like the control so is that just the manipulated the microstructure instead of the intrinsic property?
Yeah. So that, I mean, typically that's been shown, as far as I recall, only with microwaves and other types of radiation, maybe with like far IR radiation, like few microns. And so, yeah, it has to do with the fact that these approximations of N1, refractive index, and so on, are only done on a sort of macroscopic level. Okay, so when we think about the actual material that's in this, we have to think about the constituent atoms. And most of the time, we can just ignore the fact that there are atoms inside and just replace the whole material by this refractive index. But we can't do that in certain types of materials that we make, like which are called metamaterials, where now the refractive index can be so-called negative. Maybe we can have that discussion at another time about like what does it mean for negative refraction.
I think we have to look at the Maxwell equation.
Exactly. So we have to resolve the Maxwell equation for those situations. So we can't discuss it in the ray optics picture right now. Okay. All right. So any other questions about total internal reflection? Okay. So one of the things that total internal reflection is good for is for making prisms. For example, if I cut this prism at a 45-degree angle, okay, then the incident beam that comes in is always greater. If it's a normal incident, is always going to hit the surface, the glass surface at 45 degrees, right? And that angle is greater than the 42 degrees total internal reflection. So the beam will be perfectly reflected. And so this is a simple way, for example, to make a beam go 90 degrees. Okay, to bend a beam by 90 degrees, take a piece of glass and cut it into the shape, and you can get a 90-degree reflection. So this is just, an isosceles prism, right angle, which gives you the reflection. You can also build retroreflectors, same prism, just turn it over and change the direction in which you bring the beam. So here now the beam, and you cut the prism long enough so that the outgoing beam again meets another surface, okay? And this is now going to get reflected again by perfectly, and that gives you a retroreflector prism, okay? This is just an example of like things that total internal reflection gives you at these prisms, but there's lots of examples. I'll show you a couple more in a second on the slides. The other thing I want to point out also, and I don't know if I'll have time to discuss it, the math in detail, but the fact that the rays of light bend towards or away from the normal, this is responsible for phenomena like, for example, the apparent depth or bending of a spoon when you put it into the water. Because basically what's happening is that if you have, say, here water, and you have an object, in this case, the bottom of the spoon, for example, then it turns out that the rays of light that are coming are going to bend outward from the normal because they're inside the water and they're coming out of the water, right? So that's higher refractive index to lower refractive index, which is exactly this situation over here. The incident beam was bending away from the normal. So then if I project, if I'm over here observing with my eyes, okay, and I'm watching I guess I do the eyelashes right now. All right, so I over here, then the rays of light appear to be coming from an object which is raised relative to the original object, which is over here. And so the spoon, which you would have thought was going in a straight, had a straight path like that, or was made in a straight line, now appears to bend because the rays are appearing to come from an angle higher than you would expect it to be. Okay, so that's the bending of a spoon, for example, in water. It's also responsible for the fact that if you're swimming under the water and you're looking outward, you only see the world in a narrow circle of light. You might have noticed this phenomena if you ever go down to the bottom of a pool and you're holding your breath and you look out. Then you can't see the whole, ceiling or something. You only see like part of it, which is defined now by the total internal reflection angle inside the water, because you can't see the rays that are greater, that are incident, that are going out or are incident, exactly at angles such that they are above the internal reflection angle. Okay. So these are just two phenomena. I'm not going to go through the math here. It's fairly straightforward, or we can think about it if you want to, but I just wanted to tell you about those phenomena so that you're aware of what's going on. Okay. So, any questions? This? Zoom again. Okay, so here are some applications in technology for total internal reflection. So you can use them in fingerprint sensors. That's just one example. So you have your finger, you shape with micro machining techniques on your iPhone, or before it was, before we had face recognition, they were using fingerprint recognition. And so what it is basically you send a laser illumination through this little piece of glass, which has been micro machined inside, and then that reflects from the fingerprint and then comes and hits a small camera with a few pixels on it, and that is enough to build up an image of your fingerprint on the camera and capture that. Another application of total internal reflection is in optical waveguides. So this is, for example, you're all familiar with optical fibers. What I'm showing you here is a multi-mode optical fiber, and this is now the planar version of that, which means that instead of having a cylindrical object, imagine like a slab of glass with another slab of glass on it, which has a higher refractive index. Usually this is some dielectric film, which has a slightly higher refractive index than the glass. And then you can sandwich it with another piece of glass. This is often used also in many industrial applications. Again, the beam of light that comes through here is if it's making an angle greater than the critical angle, then it's going to reflect continuously and just be confined in the region of the waveguide. The same thing happens in so-called multi-mode optical fibers, which are used for a lot of applications to send light through, which is, not always in like the communication fibers. Those tend to be single mode fibers, which we'll come back to later on in the course. But at least in the multi-mode fibers, the core diameter is about 8 to 10 microns. The cladding diameter is about 250 microns. And then there's a small index contrast, very small. Okay, it's only like 0.007 difference between the inner core and the outer cladding of this fiber. But that's enough again to find a angle, which is the total internal reflection angle, and rays of light that are greater than that will get confined, and other rays which are not at that angle will not get confined. And so that's why only certain angles of light are accepted into the fiber. So you have to launch the light carefully when you're doing the experiments. But that allows us to, for example, send light over very long distances, because nowadays the commercial optical fibers have very low attenuations, especially in the infrared region of wavelengths.
So we say waveguide. So we say we are solving the Maxwell, the Maxwell equation, the electric field and magnetic field with a boundary, with a boundary condition. So how do we so at the boundary, so what boundary condition at the surface or boundary condition? We said now you said there is only one light, but it's like the magnetic field and electric field.
Yeah. So you have to match the boundary conditions at the two interfaces. All right. We'll discuss that when we do electromagnetic wave propagation. Okay. But this is just a physical picture. It's like the geometrical optics picture is enough to understand multi-mode fiber propagation.
In that case, we have the frequency cutoff.
Yeah, that's all for single mode fibers. It's more relevant. For multi-mode fiber, not quite as relevant. Yeah, there is a frequency cutoff for them as well. In our limit, we are assuming that I'm just showing you like an intuitive picture for what's going on in a multi-mode. Similarly, we can also talk about something called the total internal reflection in a gradient index waveguide. So here, instead of having one refractive index, like a step index, meaning the inside material is all of one index and the outside material is all of one index, the inside material itself has gradients of index, smoothly varying, and people know how to do that. So if you were to plot the refractive index profile, it might be like n min out here, and then it will grow to n max, and then again die away outside to n min again. Okay. So why is this useful? Well, I mean, as you can see, the path of the light is now much smoother. This has important considerations for things like the pulse dispersion as you go through a fiber. Again, I'm not going to talk about that, but again, the point is that you can model the behavior of the rays or of the light in using the ray optics formulas. And one example of Grin waveguides, we have made Grin waveguides in the lab. I mean, we use them. Grin lenses are another thing that you'll find if you open up an optical catalog. Gradient index lenses are often found, and they are very useful when you have a certain application where you want to like send the light through some longer path distance. And the other situation where this has been found in nature is in an insect. So actually, the waveguides are present here inside the compound eye of an insect. There are waveguides to take the light and direct it into the receptor, and those happen to be Grin waveguides. Okay, so it's already made in nature long before we made it. Okay, so before I go on to talk about mirrors, I'm just coming back to mirrors a little bit because I just want to say a few words about them before we move on from this topic. But any questions so far about total internal reflection, etc.? Grin waveguides? Okay. So I'm coming back to mirrors just to point out a couple things that you may or may not have observed. I think you've all observed probably. One is that due to the second law of reflection, which is that the incident angle and the reflected angle are equal, the left-handed and right-handed triads, or left hand and right hand, gets interchanged in a mirror. Okay. The reason for that is pretty straightforward. If I look at this right-handed triad, okay, so this is, imagine a person with their hand sticking out to the right. Okay, that's this picture over here. and the light is incident from here, you can think about it as into the screen in this case. And then, of course, due to the law of reflection, the component of the ray, normal to the interface, gets a minus sign, right? Basically, the light now reverses back. So instead of going inward, it's coming outward, coming back. And so what that happens is then when you draw the paths of the rays, and of course, remember that the mirror image is obtained by just extending the rays of light backward from this reflected ray backward. That's what would be observed by somebody who is observing over here. Now you see on this side, it'll look to them as if the left hand is being raised. Okay, so this is the interchange between the right and the left that happens in a mirror surface. And so I guess I'll ask you the question, maybe to think about, why is it that the top and the bottom don't get interchanged? Okay, just told you left and right get interchanged due to the law of reflection. Why don't top and bottom get interchanged? Thoughts? Here, the head isn't appearing at the feet, right? But I just told you the beam is getting reflected, and it changes the normal, or changes the direction of the propagation inwards. Yes, Howard.
Wouldn't be the shortest path to do that.
That's. But why? I mean, if I just argued that it is true for the left and right hand, that it is okay, that is the shortest path, right? As we proved by Fermat's principle. Why isn't that the same for the upper and lower parts? Is there something that's breaks the symmetry? Okay, we'll come back to it. Think about it. All right. So, very briefly, I just want to say something about how mirrors are made. So mirrors, in most situations, it's easy enough to coat a thin layer of glass on the back side with a metal. Okay, and the metal is pretty reflective, and so that protects the metallic surface. You can just cover it up or whatever, and then when you look from the front, now there will be the reflection from the metal surface. Okay, but also, as we know, there must be a reflection from the glass, right? Because we just talked about that. So there's usually a ghost reflection. So these are called second surface mirrors. That's because the metal is coated on the back side. Okay, and this is a conventional mirror. That's typical of most mirrors that you get at a household or something like that. But you may want to not have that ghost reflection, in which case you would want to buy a front surface or first surface mirrors. And what they are is simply inward. So now the metallic surface is coated on the top layer of the glass. So now there's no reflection from the glass that's coming back. Everything is just reflected, and you obviously coat it greater than something called the skin depth. We'll come back to that later on. But if it's a few microns thick, that's already more than thick enough that all the light is reflected from the first metallic surface. And but the problem then is that the metallic surface is very delicate, couple microns. It's easy to scratch or break, or if you try to clean it, it'll immediately get descaled and or it'll corrode. It's a metal. So what we often do is coat yet another very, very thin, much less than a wavelength dielectric, because we now have very good film coating technologies that allow you to coat a few nanometers or tens of nanometers of some dielectric that is hard and will protect that metallic surface. Okay, so that's one way in which mirrors are made. But another way in which mirrors are made, which we'll come back to when we discuss interference of waves, is that the mirrors can be made through a process of coating many layers of dielectrics. So even though each individual dielectric only reflects a little bit, okay, at that interface, by creating a constructive and destructive interference between the rays, we can make it so that all of the light is reflected. Okay, and you may often find this when you are very careful and you care a lot about like every little loss that you have, because mirrors made from metals, even though they're pretty reflective, the reflectivity is about 90% to 95%. So you lose about 5% of light. This doesn't seem like a big deal, but if you take something like LIGO, you're all familiar with the LIGO experiment, where there's a very powerful laser that's circulating in a cavity, and the cavity is like kilometers long, and the laser basically bounces thousands and thousands, hundreds of thousands of times inside the cavity. If you have even like a percent loss in that mirror, you basically lose all your light by the time the light does all the round trips. Even worse, you're dumping all that energy because you have a very powerful laser inside the cavity. You're dumping all that energy into the mirror, and the mirror will basically just get deformed by all the heating that's happening. Okay, so when you care a lot about the reflectivity, then we found that this is one of the best ways in which we can increase the reflectivity by like coating many layers of dielectric with very careful layers. This is all a result of all the advances that we've had both in optical physics. We understand how to make these theoretically, but also, of course, due to the film technology that we've figured out how to coat these layers of dielectrics very carefully and smoothly onto glass. And I already told you, we can make a mirror, or at least a good retroreflector, or through just total internal reflection at a prism. It's not quite as efficient because, again, as I said, you get some losses always in all these situations. Okay, so the next thing to talk about, again, very quickly, is the fact that so far I've been taking the refractive index as just a constant. Okay, as I said to you that the refractive index in glass is 1.5. Well, that is true, but not quite. Okay, it is true at like a central wavelength, but around that wavelength, the refractive index varies slightly. And as you can see, it's not much of a difference. Okay, so let's just take the visible light region, which is over here, which is this almost flat part of the refractive index. And as you can see, the absorption coefficient here is very small. And so in this wavelength region, the refractive index varies around this 1.5 region by a small amount. Okay, usually in the second or third decimal place is where the changes are happening. Okay, so what that means is that when incident light is on a piece of glass, we observe colors coming out, which is of course Newton's famous experiment where he showed that you take white light on glass and you get all these different colors, red, green, and blue. That's because, as you can see from this, wavelength increasing over here, right? Remember, wavelength increasing that's the red wavelengths, okay? And wavelength decreasing is the blue wavelengths over on this side. So the red wavelengths have lesser refractive index, blue wavelengths have greater refractive index, and that's why you can see higher angles by which these red and green and blue wavelengths are differing. Okay. So then I have a question for you. Now, based on the few things that you've learned, and this is a quiz that should be open on your canvas. So I want you to talk to your neighbor and answer this question. Okay. So open up your phones or whatever if you like, and on canvas, but you can discuss first with your friend, colleague. When the index of refraction is dependent on wavelength, what will happen to the white light that is incident on a retro-reflecting 45-degree prism? So remember, we talked about the 45-degree prism and how we can make a retro-reflector from it. So, and I will just say that the refractive index of red light in the glass is 1.51 and blue is 1.53. And so the question for you is the outgoing light still retro-reflected, but the different colors will be spread out? So they want no, so now the beam coming backward will no longer be white. It'll have all the different colors spread out. Or will it be retro-reflected and still be white? Light will be transmitted straight through and the colors will be spread out. The light will be sent in a different direction, neither straight nor retro-reflected, and will be white. So why don't you talk to your friend, colleague over there and decide what the answer is? I'll give you a couple minutes to think about it.
Is this
the geometry is what I drew on the Back there, is it still there?
It's going to depend.
Yeah, it's still there, but I want to be the question. So, if you can't see here, I'm sorry. It's basically this geometry. Incident light reflected here. This is a 45-degree prism, and then this is another reflection over here, and the beam goes back. Yeah. So the question is, will that beam going backward, will the beam still go forward, or will it be white, will it be red, blue, etc.? But that's a question.
That was like that's I know that. Yeah. Sure.
Yeah, sure. Absolutely. I totally get that. But what's the thing?
My first thought is that there will be dispersion. Yeah, that's just my intuition. I don't know why I think
So to refine your thinking a little bit more, can you consider what happens to different colors in each of those interfaces? Maybe
Arc sign.
they would disperse,
Yeah.
right?
Yeah.
Would they?
For either.
That is the what is causing the reflection? I'll let you repeat it. So let me hear how it's working. Any color. If you're a team or four of you. That's all. What's your thought process?
I think I'm reading.
To speak, okay.
Yes, I think it's B because so we can calculate the
Well, hold on. Don't tell the answer. Okay, you have an answer for B. Okay. I want to hear the thought process. Okay, before we go to the answer. What is it? Uh-oh. Somebody says it. You know the B and say, let me talk.
Why don't you think it spreads out?
That's a good one.
Let's say it spreads
here. Over there.
Yeah, like
So then
it's fun. Like my thought is like this is not red is here. It's here. It depends on that's you kind of
the fact that different colors have different refractions.
That's right.
That seems to be
It's staying exactly. So yeah, that makes sense. I don't know why that's exactly. I was for study thinking in my head. But the comment, this only says what if it yeah, I think it doesn't because one of them is trouble faster. That's what I'm saying. I forgot what. Probably and if I were and equals to 100 in this direction. Okay, that makes sense. That makes sense. Even if I think yeah.
All right, very good. Okay, so hopefully you all entered your answers. I'm curious to see the answers.
Oh, I couldn't find it on Stan.
What?
I cannot find it.
Let's see. Did it not show up?
Yeah.
Oh, I see. I didn't find it.
Yeah, it's quiz 7. I mean, lecture 7, quiz 1.
Yeah, I think I saw the 7.
You see that?
Yep.
Everyone? Okay. Oh, you can see it now.
You're gonna be there.
Okay, here, lecture 7, quiz 1. Everyone see that? Okay.
Right, yeah.
All right. So if you've all entered your answers, I'm curious to see. Still reflector, still white. 9 to 5. Okay, very nice. Okay, interesting. Okay. But I feel like there are more people. Wait a minute. Some of you are just waiting to hear the right answer before you put it in. That's not fair. That's not fair to your colleagues or to me. Come on now. Let's enter it now. I want to see this number go up. Yeah. That's definitely more than 14. I don't know exactly how, but I can count that there's more than 14 here.
I wrote I did like ABC.
So come on. Let's see that number before I otherwise I'm just going to have to close the quiz now and you won't get a chance to enter your answer. I don't like to do it. Feels like I should. Okay, I'm going to edit this and close the class. It available.
State that.
Doesn't let me do it. Okay, I don't want to waste.
I think we should just take that.
Okay, anyway, all right, whatever. Okay, let's see the numbers. Okay, a little bit. All right, I think mostly everyone has their answer. So the answer is B, indeed, it is correct. Okay, but so I like how you were thinking. Some of you are like by symmetry, 2, the beam goes in, the beam comes out. That's actually a principle. It's Fermat's principle of reciprocity. Okay, kind of you can argue that by reciprocity, that if I run everything backward, I should still get a beam coming back that's white, right? Everything should look symmetric in time. So in that sense, it should all be also white. So that's one way to think about it. The other way to think about it is, and I heard somebody, maybe Abraham, you were starting to answer it. Maybe you want to say what is your reasoning for why it's white?
My reasoning is so the critical angle. The critical angle is arc sine 1/1 is so the critical angle 1/1 and
1/2, right?
And then compare that with a 45
Exactly. Perfect. Yeah, that's exactly the other way to think about it, which is that if you calculate the critical angle for the 2 refractive indices that I gave you, N1, N red, and N blue, you find out that both of them have angles that are smaller than the 45 degrees, which means both red and blue will get reflected equally at the interface because they are both greater than the critical angle. And therefore, both red and blue will be reflected, and obviously it will happen at the second place as well, and therefore the beam will remain white as it comes. Okay, excellent. Okay. Let's see, how much time? A few minutes. Okay. So let's talk a little bit. Actually, I just motivated that in some sense. So we have talked about Fermat's principle a little bit. So let's just talk about some corollaries of Fermat's principle. So I'm going to stop the presentation. Need that anymore. So in just a couple of minutes, I want to say a few things about Fermat's principle. Okay. before we knew about waves and before we started thinking about the refractive index in a medium as occurring due to the phase velocity change in the medium and due to the phase shift, due to the scattered light having a different phase than the incident light, Fermat's principle was really helpful because it gave a meaning to that factor that Snell came up with, right? You know, when Snell did his experiments, all he did was something like plot sine theta 1 versus sine theta 2, see that there was a constant slope to that relationship and say, this means that there's some factor which I call refractive index that is a constant when the media are the same. So like, you know, water and glass, he also did it with gases, you know, and he did it with like air, whatever, air and glass and water, etc. He did all these combinations to show that it was a constant for most of these situations. But people didn't really have a good explanation for why this should matter. So in a sense, the fact that Fermat was the first to say that actually the refractive index is a measure of the speed of light, because he formulated this principle of least time or greatest optical or minimum optical path length, and he gave a meaning to this refractive index by saying it's the time. The time is inside the material is changing because of this refractive index. So in that sense, Fermat's principle gives us a new way of thinking about, at least back then, of thinking about why this refractive index, what is it actually telling you about the medium or about light in that medium, okay? Secondly, another sort of consequence of Fermat's principle was that he was able to now predict what would happen if you took 3 different media, okay? So again, you know, because Snell's law was just like this relationship between angles, you know, he couldn't really say that there's no prediction. You know, there's no prediction for saying what now happens if I take air and glass and then water, you know, or air, water, and then glass, or, you know, things like that. He couldn't really make a prediction. But with Fermat's principle, we can clearly see, okay, you know, we can make a prediction about what happens in those situations to the refractive index. He could predict that the refractive index ratio, because, you know, if V1 is C over N1 and V2 is C over N2, and now V3 is C over N3, he can now give a prediction for the ratio of the refractive indices between N2 and N3, right? Simply by making measurements with respect to N1, right? So he could find N1 to N3, N1 to N2, and from that predict what would happen to N2 to N3 without having to make the measurement. So that's the power of a principle like that. Yes.
So this is a discrete one, but if we have a continuum of the refractive indices, then it changes like with 3D and R. So we're showing at the point and when we find the trajectory, and then this just fails, we have to go back to all the way to the functional and find the minimum of the functional value.
Or you can break up the medium into small pieces where the refractive index is a constant and solve a differential equation. You can do it both ways. Okay. Yeah. I'll give you a homework example like that. Okay. All right. And okay, I'm out of time, but I'll just state the principle of reciprocity. I'll just state that and we'll talk about it in the next class. This is another consequence of Fermat's principle, and it came about because of this understanding of the least time argument. Because it's obviously if I go from point A to point B in the least time, right, through some path, then by reversing the flow of time, right, I must be going from point B to point A in the least amount of time as well. Okay, so and there are many consequences. For example, the fact that if I send a beam of light through a glass like this, okay, and if I know that this beam of light does something like this, which you have all seen in your labs, now you could ask, what happens if I reverse the flow of the light? Will it now get displaced back up here, or will it get displaced down here? Right? You could ask that question, like, oh, maybe the displacement should go the other direction. But no, by Fermat's principle, we know that between the point A and this point B over here, the least amount of time is always taken by this path, so the beam must come back like this without knowing anything about refractive index or the angles. We don't need to calculate the geometry. We can just predict that that must be the least time. Okay, I'll stop there and we'll continue this in the next. Yeah. Yeah. It should be in your, it should be there. Yeah, in your group. Yeah, whoever your partner is.